Here's what we're going to do today. When we solve a linear program through the simplex method, we may run into some abnormal situations. We may run into some anomalies. What kind of anomalies can we run into when we solve a linear program through the simplex method? The linear program that we're solving could be infeasible. The linear program that we're solving could be unbounded. We can find feasible solutions that make the objective value as larger and larger without violating any of the constraints. Linear program could be unbounded. Or linear program could have multiple optimal solutions. So when we solve a linear program through the simplex method, we may run into some anomalous situations. We can have the linear program infeasible. We can have linear program unbounded. We can have linear program have multiple optimal solutions. And in this lecture, we're going to discuss how we can detect these anomalies when we solve a linear program through the simplex method. How can we detect whether the linear program is infeasible? How can we detect whether the linear program is unbounded? How can we detect whether the linear program we're solving has multiple optimal solutions? Okay. We already talked about how we can detect whether the linear program is infeasible. We had the phase one linear program for it, right? So give me a linear program that you want to solve. If I want to check whether this linear program is infeasible or not, give me the linear program that you want to solve. If I want to check whether this linear program is infeasible or not, I construct the phase one linear program corresponding to this linear program and solve the phase one linear program. If at the optimal solution of the phase one linear program, the decision variable u takes value strictly positive, then I know that the linear program that I would like to solve, the original linear program that I would like to solve, is infeasible. So we have the phase one linear program to detect whether the linear program that you give me is infeasible or not. So we know how to detect infeasibility. So in this lecture, we're going to talk about then how we can detect whether the linear program that we're solving is unbounded or not, and how we can detect whether the linear program that we're trying to solve has multiple optimal solutions. So those are the two anomalies that we're going to see how we can detect. Okay, so let's first talk about how we can detect whether the linear program that we're solving is unbounded. Can I find feasible solutions that make the objective function of my linear program as large as I want without violating any of the constraints? How can I detect whether the linear program I'm solving is unbounded? So let's take an example for that. Let's imagine that we're trying to solve a linear program that looks like this. Maximize 4x1 plus 6x2 minus 3x3, subject to 2 less than or equal to constraints. 2x1 plus x2 minus 2x3 is less than or equal to 3. 3x1 plus 3x2 minus 2x3 is less than or equal to 4. All of our decision variables are non-negative. And let's try to solve this linear program through the simplex method. And let's see if and how the simplex method detects whether this linear program is unbounded or not. Whether we can find feasible solutions that make the objective value larger and larger and larger without violating any of the constraints. Okay, so let's solve this linear program through the simplex method, business as usual. Let's construct the first system of linear equations. 4x1 plus 6x2 minus 3x3 is my objective function row. And then the first constraint row, 2x1 plus x2 minus 2x3 plus the first slack variable equals 3. And the second constraint, 3x1 plus 3x2 minus 2x3 plus the slack for the second constraint, w2 is equal to 4. Let's solve this linear program through the simplex method, business as usual. Our basic variables are w1 and w2. So the solution we read to the system is w1 is equal to 3, w2 is equal to 4. X's are all zeros, x1, x2, x3 are all zeros. X1, x2, x3 are zeros, so z is 0. And our basic variables are w1 and w2. Our non-basic variables are x1, x2, x3. Good. We're trying to maximize the objective function in this linear program. Is there any decision variable that we can increase to make the objective function larger? Yes, if we increase x2, it's got a positive objective function coefficient. The objective function is going to get larger, and this is the one that gives us the biggest bang for the buck. So let's go ahead and increase x2. Okay. So the question is, how much can we increase x2 before we run into infeasibilities? From the first constraint, I can increase x2 all the way up to 3 before w1 turns negative. From the second constraint, I can increase x2 all the way to 4 over 3 before w2 turns negative. So here we can increase x2 all the way to 3 before we get in trouble. Here we can increase x2 all the way to 4 over 3 before you get in trouble. So we're going to increase x2 all the way to 4 over 3. So we increase x2 up to the minimum of 3 and 4/3. So that is 4/3. So the binding value for x2 happens in the second constraint. So we're going to do row operations such that x2 appears only in the second constraint row. So do row operations such that x2 appears only in constraint 2. The binding value for x2 appears in the second constraint, so the row operation such that x2 appears only in the second constraint row. Good, let's do those. I want x2 to disappear from the objective function row. Take the second constraint row, multiply by -2, add it to the objective function row, so x2 disappears from here. And I want x2 to disappear from the first constraint row, take the second constraint row, multiply it by -1/3, add it to the first constraint row, so that x2 disappears from the first constraint row as well. Good. Let's do those row operations. Okay. Take the second constraint row, multiply it by -2, add it to the objective function row. 3 times -2 is -6x1 plus another 4x1. That is going to give me -2x1. 3 times -2 is -6x2 plus another 6x2. x2 goes away. That's what I'm trying to do. -2 times -2 is plus 4x3 minus another 3x3. That's going to give us plus x3. No w1, no w1. W2 times -2 is -2 W2 plus no W2. That's going to give us -2 W2. And on the right-hand side, 4 times -2 is -8. Z on top of that, Z minus 8. Let's take care of the first constraint row, multiply the second constraint row by -1/3, add it to the first constraint row. 3 times -1/3 is -1x1 plus another 2x1. That is going to be an x1 here. 3 times -1/3 is -x2 plus another x2. x2 goes away. That's what we're trying to do. -2 times -1/3 is 2/3x3 minus another 2x3. 2/3 minus another 2x3. That is 2/3 minus 6/3. That's going to give me -4/3x3. No W1 times -1/3. That's no W1 plus another W1 on top of that. That's a W1. W2 times -1/3 is -1/3 W2 plus 0 W2 -1/3 W2. And on the right-hand side, what do we have? 4 times -1/3 is -4/3 plus another 3. 3 minus 4/3, that's 9/3 minus 4/3. That's a 5/3. Good. And lastly, I would like x2 appear in the second constraint row with a coefficient of 1. So let's multiply the second constraint row across by 1/3 so that x2 appears with a coefficient of 1 here. So this times 1/3 is x1. This times 1/3 is x2. This times 1/3 is -2/3 x3. No W1 plus 1/3 W2 is equal to 4/3. Okay. Good. So this is the system that we reach at the next iteration. Let's write the solution corresponding to the system. Our basic variables are W1 and X2. So W1, the solution we read as W1 is 5/3. X2 is 4/3. And X1, X3, and W2, X1, X3, and W2 are all 0. Z is equal to 8. And let's write down what our basic variables and non-basic variables are. Our basic variables are W1 and X2. And our non-basic variables are X1, X3, and W2. Great. Did we reach the optimal solution? Is there any decision variable that we increase to make the objective value larger? Yes, we can increase X3 to make the objective value larger. So let's go ahead and increase X3. How much can I increase x3 before I get in trouble? How much can I increase x3 before I get in trouble? From the first constraint row, x3 appears here with a negative objective function coefficient. So so that signals that I can x3 as much as I want without w1 turning negative. So we covered that in one of the previous lectures. x3 appears in the first constraint row with a coefficient that's negative. That means that I can increase x3 as much as I want without the danger of w1 turning negative. If you want to refresh your mind, let's try to repeat that argument. Here right now, w1 equals 5 over 3, and x3 is equal to 0. Here right now, w1 equals 5 over 3, and x3 equals 0, and I'm increasing x3, okay? So right now, x3 is 0, w1 equals to 5 over 3. If I increase x3 to, let's say, 3, this is going to be a minus 4, then w1 has to be equal to 4 plus 5 over 3, such that minus 4 plus 4 plus 5 over 3 is going to give me 5 over 3. If I increase x3 to 100, then this is going to read minus 400. So then w1 has to be equal to plus 400 plus 5 over 3, such that minus 400 plus 400 plus 5 over 3 is going to be equal to 5 over 3. If I increase x3 to 3 million, this is going to be minus 4 million, so that w1 has to be equal to plus 4 million plus 5 over 3, so that minus 4 million plus 4 million plus 5 over 3 is going to be equal to 5 over 3. So now we see from this argument that since x3 sits here with a negative objective, a negative constraint coefficient in the first constraint, from perspective of the first constraint, I can increase x3 as much as I want without w1 turning negative. On the other hand, okay? Let's look at the second constraint. How much can I increase x3 before x2 turns negative? The same idea. x3 appears here with a negative objective. x3 appears in the second constraint row with a negative constraint coefficient. So now I can increase x3 as much as I want without the danger of x2 turning negative. If I increase x2 to 3,000, this becomes minus 2,000. It's such that these two things add up to 4 over 3. This is minus 2,000, so x2 has to be equal to plus 2,000 plus 4 over 3, so that plus 2,000 plus 2 over 3 plus 2,000 plus 4 over 3 minus 2,000 is going to add up to 4 over 3. So again, whenever the decision variable appears with a negative coefficient in a certain constraint row, we can increase that decision variable as much as we want without running into trouble. So then, since x3 appears here in the first constraint row with a negative constraint coefficient, we can increase x3 as much as possible, as much as we want, without w1 turning negative. Since x3 appears with a negative constraint coefficient in this constraint, we can increase x3 as much as we want without x2 turning negative. So we can increase x3 as much as we want without w1 or x2 turning negative. So now what do we have? Here's the decision variable x3. Each unit of increase in x3 increase the objective value by 1 unit. And from the constraint, I can increase x3 as much as I want without getting in trouble. So I can increase x3 all the way to as much as I want. That would make the objective value as large as I want. And I would never violate any feasibility. Okay, so this is how we detect. So then this linear program that we're trying to solve has unbounded solution, has unbounded. This linear program that we're trying to solve is unbounded. This LP is unbounded. So now what's the moral of the story? If at any iteration of the simplex method, if there exists a non-basic variable with a strictly positive objective function coefficient, so that we can increase that non-basic variable to make the objective larger and larger. At any iteration of the simplex method, if there's a non-basic variable with a strictly positive objective function coefficient, but all constraint coefficients are negative or 0, then the linear program that we're trying to solve is unbounded. So this is the moral of our story. Moral: at any iteration of the simplex method, if we have a non-basic variable with strictly positive objective function coefficient, and all negative or 0 constraint coefficients, then the LP is unbounded. Like in this example, we can increase x3 to make the objective value larger and larger. From the perspective of the first constraint, since the coefficient of x3 is negative, we can increase x3 as much as I want without W1 turning negative. From the perspective of the second constraint, we can, since the coefficient of x3 is also negative in the second constraint, we can increase x3 as much as I want without x2 turning negative. So then from the perspective of the constraints, we can increase x3 as much as we want without getting into trouble. And for each unit of increase in x3, objective function gets larger by 1 unit. So increase x3 as much as you want without getting in trouble. And each unit of increase in x3 is going to make the objective value larger by 1 unit. So this linear program we're looking at is unbounded. So again, the moral of the story is at any iteration of the simplex method, if we have a non-basic decision variable with a strictly positive objective function coefficient, so that we can increase that non-basic variable to make the objective value larger and larger. And this non-basic variable has all negative and 0 constraint coefficients, so that we can increase that non-basic variable without getting into any trouble, then our linear program we're trying to solve is unbounded. Okay. So you may have bought my argument, or you may not have bought my argument. What we're going to do next is that we're going to construct a concrete solution to this linear program that we're trying to solve, such that you're going to see undeniably that this linear program, I can come up with as large of a linear program, as large of an objective value that I want for this linear program without violating feasibility. Okay, so we're going to concocted a concrete solution to our linear program such that we can make the objective value for our linear program as large as we want without violating feasibility, so that you can really see that this linear program that we're trying to solve is unbounded. Okay, good. So here's how we're going to concoct that solution that's going to undeniably prove us that this linear program is unbounded. So let's look at the system of linear equations from which we saw that the linear program is unbounded. What did we do? We're sitting at the current solution, W1 is equal to 5/3, X2 is equal to 4/3, and we're increasing X3. Let's increase X3 to some large number, T. Okay. So let's say for some large T greater than or equal to 0, consider the following solution. To the linear program. We're increasing x3 to t, to the value t. So let's say x3 takes the value t. That's my t. Good. From the first constraint row, so right now at the beginning, what? X3 was 0, W1 is equal to 5/3. If I increase x3 to all the way to t, to make sure that these two guys are adding up to 5/3, W1 has to be equal to 5/3 plus 4/3 times t. Okay. So now let's set W1 to be 5/3 plus 4/3 times t. Again, I'm reading this from the last system of equations. We're increasing x3. If I increase x3 all the way to some large number t, this is minus 4/3 times t. To make sure that these two guys are adding up to 5/3, W1 has to be equal to 5/3 plus 4/3 times t. Likewise, I'm increasing x3. If I increase x3 all the way to t, I'm going to make up for an increase in x3 by playing around with x2, this basic variable. So if I increase x3 all the way to t, that is minus 2/3 times t. Then x2 has to be equal to, put this guy to the other side, x2 has to be equal to 4/3 plus 2/3 times t. So set x2 to be 4/3 plus 2/3 times t, and keep x1 and w2 at 0. Let's see what this solution is going to do for us. Let's see if this solution is feasible to the linear program that we're trying to solve. Check that this solution is feasible to the LP. Let's check the constraints of this linear program at this solution. 2 times x1 plus x2 minus 2 times x3. What is it? 2 times x1 is 0, 2 times 0, plus x2. x2 is given by 4/3 plus 2/3 times t, minus 2 times x3, minus 2 times x3 is given by t. Let's do the arithmetic. Let's do the arithmetic. That is 4 over 3, that's a 0. 4 over 3 plus 2 over 3t minus 2. 2 over 3 minus 2 minus 3 is equal to 6 over 3. That's going to give us 2 over 3 minus 6 over 3 minus 4 over 3t. For t greater than or equal to 0, is 4 over 3 minus 4 over 3t less than or equal to 3? Yes. This is 1.333. 1.33 minus some number is always going to be less than or equal to 3. Good. So then no matter what the value of t is, this solution satisfies the first constraint. Let's check the second constraint. 3 times x1, 3 times x2, minus 2x3. What is it? 3 times x1 is 0, plus 3 times x2. x2 is this much. Minus 2 times x3, minus 2 times x3 is t. Let's compute that. That's a 0. 3 times 4 over 3 is 4. 3 times 2 over 3 is 2t, minus another 2t, that's 0. So this computes to a 4. Is 4 less than or equal to 4? Yes. So the first constraint checks, second constraint checks. And my decision variables have to be non-negative. x1 is 0. That is greater or equal to 0. x2 is 4 over 3 plus 2 over 3t. When t is greater than or equal to 0, this number is greater than or equal to 0. So this checks, and lastly, x3 is t. When t is greater than or equal to 0, of course, x3 is greater than or equal to 0. So this solution that we concocted, no matter how large the value of t is always feasible. The left-hand side of the first constraint at this solution, we get 4 over 3 minus 4 over 3t. No matter how large t is, that is less than or equal to 3. The left-hand side of the second constraint at this solution is 4. That's less than or equal to 4 always. And no matter how large t is, my decision variables are always reading to be greater or equal to 0. Great. So this solution that we concocted is always feasible. Next thing we do is let's check the objective value provided by the solution. That is what? 4x1 plus 6x2 minus 3x3. Let's check the objective value provided by that solution. x1 is at the solution we concocted is 0. 4 times 0 plus 6 times x2 is this much at the solution we concocted. Minus 3 times x3. x3 is equal to t at the solution we concocted. That's a 0. 6 times 4 over 3, that's 24 over 3, that's an 8. 6 times 2 over 3t, that would be 12 over 4, that's a 4t. Minus another 3t, 8 plus t. So that's a t. 6 times 4 over 3 is 24 over 3, that's an 8. 6 times 2 over 3t, that's 12 over 3t, that's 4t, minus another 3t, so that's a plus t. So what we see is that no matter how large t is, this solution that we concocted is always feasible to my linear program, and it gives me an objective value of 8 plus t. So then choose t to be 8 billion. The solution that we concocted is going to be feasible, and the objective value that we get is going to be 8 plus a billion. Choose t to be trillion, then the solution that we concoct in this fashion is going to be feasible to our linear program, and the objective value that we get is 8 plus trillion. So you can choose t as much as you want, while the solution that you get is still going to be feasible, and you get an arbitrarily large value. So this is very concretely showing us that the linear program that we're dealing with is unbounded. And of course, to concoct the solution, to sort of figure out what this solution should look like to proving feasibility, we had to look at the last system of equations that we obtained when we solved the linear program. We had to look at system of equations that we obtained where we detected the unboundedness. Good, so this is how we detect unbounded linear program. At any iteration of the simplex method, if we have a non-basic variable whose objective function coefficient is strictly positive, and all constraint coefficients of this non-basic variable is negative or 0, then the linear program that we're dealing with is unbounded. Okay. if at any iteration of the simplex method, we have a non-basic variable such that the objective function coefficient of this non-basic variable is strictly positive. So we can increase that non-basic variable to make the objective function larger and larger. And if all the constraint coefficients of this non-basic variable are 0 or negative, then we can increase the value of this non-basic variable as much as we want without getting into trouble. Then the linear program that we're dealing with is unbounded. So this is how we detect unboundedness of a linear program. So now let's talk about how we can detect multiple optimal solutions when we're solving a linear program through the simplex method. And again, we're going to see that on an example. Let's say that we're solving a linear program that looks like this. Maximize 7x1 plus 12x2 minus 3x3, subject to these two inequality constraints, and all of our decision variables are restricted to be non-negative. Let's see how the simplex method allows us to detect multiple optimal solutions along the way. So let's solve this linear program through the simplex method as we know it. The objective function rho, first constraint rho, good. Our basic variables are W1 and W2. So the solution we read is W1 equals 1, W2 equals 2. Good. X1, X2, and X3 are 0. Z is equal to 0. Basic variables are W1 and W2. Non-basic variables are X1, X2, X3. Good. Looking at the objective function rho, we're going to increase X2 to get to a better objective value. So let's increase X2. How much can we increase X2? From the first constraint, this is an 8. From the first constraint, we can increase X2 all the way up to 1 over 8. From second constraint, we can increase X2 as much as we want without getting in trouble because it's got a negative coefficient here. So then we can increase X2 all the way up to 1 over 8. In that case, the minimum value of X2 is determined by the first constraint. So do row operations such that X2 appears only in the first constraint. Good. To make sure that X2 appears only in the first constraint row, take the first constraint row, and multiply it by minus 12 over 8. What is minus 12 over 8? Minus 12 over 8 cancelled by 4, that is minus 3 over 2. Good. And to make X2 disappear from the second constraint row, take the first constraint row and divide it by, multiply it by 3 over 8 added to the second constraint row. So let's do those row operations and see where we get. Take the first constraint row, multiply it by minus 3 over 2 added to the objective function row. Let's do the arithmetic. 6 times minus 3 over 2, that is going to give us minus 18 over 2. So that's a minus 9 plus another 7x1. That is going to give us minus 2x1. Good. 8 times minus 3 over 2, it's going to give us minus 24 over 2. That's minus 12 plus another 12x2. X2 goes away. That's what we're trying to do. Minus 2 times minus 3 over 2, that's going to give us plus 3x3. Minus 3x3 on top of that, x3 goes away. W1 times minus 3 over 2 is minus 3 over 2 W1 plus no W1. That's going to give us minus 3 over 2 W1. W1. No W2, no W2. And on the right-hand side, 1 times minus 3 over 2 is minus 3 over 2, Z minus 3 over 2. Let's take care of the second constraint row, multiply the first constraint row by 3 over 8 and add it to the second constraint row. 6 times 3 over 8. 6 times 3 over 8 is going to give us 18 over 8. That is a 9 over 4. Minus another 3 on top of that. 9 over 4 minus 12 over 4, that's going to give us minus 3 over 4 x1. Good. 8 times 3 over 8 is going to give us plus 3x2 minus 3x2. X2 goes away. That's what we're trying to do. Minus 2 times 3 over 8, that is going to give us minus 3 over 4. Plus another 1, minus 3 over 4, plus another 1. That is minus 3 over 4 plus 4 over 4. That's 1 over 4 x3. Good. W1 times 3 over 8 is 3 over 8 W1 plus no W1. That's 3 over 8 W1. No W2 plus W2, W2. And on the right-hand side, 1 times 3 over 8 is 3 over 8 plus another 2 on top of that. 3 over 8 plus 2. That is 3 over 8 plus 16 over 8. That is 19 over 8. Good. And I want x to appear in the first constraint row with a coefficient of 1 and nowhere else. So multiply the first constraint row by 1 over 8 so that x2 appears with a coefficient of 1. 6 times 1 over 8 is 6 over 8. That is 3 over 4 x1. x2 multiplied by 1 over 8. That is minus 1 over 4 x3. Multiply that by 1 over 8. 1 over 8 w1. Multiply that by 1 over 8. 1 over 8 on the right-hand side. Okay, good. This is the next system we reach. What are our basic variables? X2 and W2. And what is the solution we read here? X2 is equal to 1 over 8. W2 is equal to 19 over 8. X1, X3, and W2 are 0. And Z is equal to 3 over 2. And let's mark our basic variables. Our basic variables are X2 and W2. And our non-basic variables are X1, X3, and W2. Great. Did we reach the optimal solution? Is there any non-basic decision variable we can increase to make the objective value better? No. All the objective function coefficients are 0 and negative. So this is the optimal solution to the linear program. There's no decision variable we can increase to make the objective value better. They all have negative or 0 objective function coefficients. There's no basic decision variable that we can increase to make the objective value better. So we reach the optimal solution to the linear program. Good. But now we have this non-basic variable x3. Its objective function coefficient is 0. So we have this non-basic decision variable x3. Its objective function coefficient is 0. That means that if I increase that non-basic decision variable x3, the objective value is not going to go up, but it's not going to go bad either. It's not going to go down either. So it's completely okay if I increase x3. The objective function is not going to get better, but it's not going to go worse either. So let's just, for fun, let's go ahead and increase the value of the non-basic decision variable x3, and let's see where it gets us. Okay. So let's say in the last system of equations, the non-basic variable x3 has objective coefficient 0. So increasing x3 doesn't make the objective value better, but it doesn't make the objective value worse either. Let's, for fun, let's go ahead and increase the value of x3 and let's see what happens. So increasing x3 does not make the objective value better, but it doesn't make the objective value worse either. Let's go ahead and for fun, let's just go ahead and for fun, let's increase the value of x3. Just for fun. Let's go ahead and increase x3. So we're increasing x3. If I increase x3, From the first constraint row, x3 appears with a negative coefficient over here. I can increase x3 as much as I want without x2 turning negative. From second constraint row, I can increase x3 all the way to 19 over 8 divided by 1 over 4. 19 over 8 divided by 1 over 4. That's 19 over 2. From second constraint row, I can increase x3 all the way to 19 over 2 before w2 turns negative. So the second constraint row is binding. We're going to do row operation such that x3 appears only in the second constraint row. So increase x3 all the way up to 19 over 8 divided by 1 over 4. That's 19 over 2. So do row operations such that x3 appears only in the second constraint. Let's do those row operations. So if I want to get it, so I want to make sure that x3 appears only in the second constraint row with a coefficient of 1. I want x3 to disappear from the objective function row, but it's already gone from the objective function row. I don't need to worry about it. And I want x3 to disappear from the first constraint row. So take the second constraint row, multiply it by 1, add it to the first constraint row so that x3 is going to disappear from the first constraint row. Write the objective row as it is because x3 is already gone from the objective row. Let's take the second constraint row and add it to the first constraint row. Minus 3 over 4x1 plus 3 over 4x1, x1 goes away. 0x2 plus another x2, then x2. 1 over 4x3 minus 1 over 4x3, x3 goes away. 3 over 8 w1 plus 1 over 8 w1. 3 over 8 plus 1 over 8, it's 4 over 8, that's 1 over 2 w1. w2 plus 0 w2, that's w2. And on the right-hand side, 19 over 8 plus 1 over 8, that is 20 over 8, 20 over 8, 20 over 8, that is 5 over 2, if you cancel by 2, if you simplify by 2. Okay, and we also want x3 to appear in the second constraint row with a coefficient of 1. Let's multiply the second constraint row by 4. What we get is 3x1 plus x3 plus 3 over 2 w1 plus 4w2 is equal to 19 over 2. Multiply everything by 4. This is the next system of equations we get. Good. What are our basic variables? x2 and x3. So the solution we read is what? x2 is equal to 5 over 2. x3 is equal to 19 over 2. x1, w1, and w2 are non-basic variables. They're all 0. And z is equal to still 3 over 2. And our basic variables are here is x2 and x3. Non-basic variables are x1, w1, w2. Is this an optimal solution to the linear program that we're trying to solve? Yes, this is also an optimal solution to the linear program that we're trying to solve. All the objective function coefficients are 0 or non-negative. So this is also an optimal solution to the linear program. So then the observation is that if at the final iteration of the simplex method, this was our final iteration of the simplex method, if you have a non-basic variable with a 0 objective function coefficient, then the linear program that we're trying to solve has multiple optimal solutions. The moral of the story is that if at the final iteration of the simplex method, if you have a non-basic variable with a 0 objective function coefficient, that means that we can increase the value of that non-basic variable. It wouldn't make the objective value worse, but it wouldn't make the objective value better, but it wouldn't make the objective value worse either. So if at the final iteration of the simplex method, we have a non-basic variable with 0 objective function coefficient, then the linear program that we're trying to solve has multiple optimal solutions. This is one optimal solution that we had, and this is another optimal solution we had. In this optimal solution, x1 was 0, x2 is equal to 1 over 8. In this, x3 is equal to 0. And this optimal solution, x1 was 0, x2 is equal to 5 over 2, and x3 is equal to 19 over 2. So we have two possible optimal solutions. So the moral of the story is, at the final iteration of the simplex method, if you have a non-basic variable with zero objective function coefficient, then we have multiple optimal solutions. Good. That's the moral of our story. If at the final iteration of the simplex method, if you have a non-basic variable with a zero objective function coefficient, increasing that non-basic variable does not improve the objective value better, but it doesn't make the objective value worse either. So then if you go ahead and increase that non-basic variable, you reach another optimal solution. So our problem has multiple optimal solutions. Okay, so this is how we detect multiple optimal solutions. And also, as we've seen before a second ago, this is also how we detect unbounded linear programs. Okay, so to recap, how do we detect unboundedness? At any iteration of the simplex method, at any intermediate iteration of the simplex method, if you have a non-basic variable with a strictly positive objective function coefficient and all zero and negative constraint coefficients, if at any iteration of the simplex method we have a non-basic variable with a strictly positive objective function coefficient and all zero or negative constraint coefficients, then we have an unbounded linear program. If at any iteration of the simplex method, we have a non-basic variable with a strictly positive objective function coefficient, so that we can increase that non-basic variable to make the objective value larger and larger. And if this non-basic variable had all negative or zero constraint coefficients, so then we can increase that non-basic variable without getting into any infeasibility trouble, then we have an unbounded linear program. On the other hand, to detect multiple optimal solutions, if at the final iteration of the simplex method, if you have a non-basic variable with a zero objective function coefficient, then we have multiple optimal solutions. If at the final iteration of the simplex method, if you have a non-basic variable with a zero objective function coefficient, then we can increase that non-basic variable without improving or degrading the objective value. That reaches us to another optimal solution. So if at the final iteration of the simplex method, we have a non-basic variable with a zero objective function coefficient, then we have multiple optimal solutions. Okay, so this is how we detect unbounded linear programs and multiple optimal solutions. Good. So now we know how to detect multiple optimal solutions. We know how to detect unbounded linear programs. Also, we know how to detect whether the linear program we're trying to solve is infeasible or not. That is from the phase one linear program. So we're going to talk about one more anomaly, one more interesting thing that could happen when we're solving a linear program through the simplex method. So we're going to talk about one more interesting anomaly thing that could happen when we're solving a linear program through the simplex method, and that's called degeneracy. Okay, what is degeneracy? When we're solving a linear program through the simplex method so far, all of our basic decision variables took strictly positive values. When we're solving a linear program through the simplex method so far, all of our basic decision variables took strictly positive values. Okay, but when you solve a linear program through the simplex method, it may be the case that some basic decision variable takes exactly the value zero. So when you reach a solution during the course of the simplex method, where some basic decision variable takes value zero, we call that solution as the degenerate solution. Okay. So when the simplex method runs into a degenerate solution, it may do a few iterations during which the objective value doesn't improve at all. So the simplex method may spin its wheels for a while without making any improvements in the objective value. But eventually, you get out of that rut, you get out of that spinning your wheel situation, you eventually get to the optimal solution. Okay, so that's the last anomalous thing we're going to talk about during the course of the simplex method. Again, that's called degeneracy. What is degeneracy? During the course of the simplex method, we may run into a solution where a basic variable takes exactly value to zero. If that is the case, we say that the solution we run into is degenerate. If the simplex method runs into a degenerate solution, it may do a few iterations spin its wheels without improving any of the objective value at all. But eventually, it gets out of that spinning its wheels situation. It gets to the optimal solution eventually. Let's try to see degeneracy in action in a particular example. Let's say that we're solving a linear program that looks like this. Maximize 12x1 plus 6x2 plus 16x3, subject to these inequality constraints, two inequality constraints, and all of our decision variables are non-negative. So let's solve this linear program through the simplex method and see what kind of iterations we run into. Here is the system that we start with. 12x1 plus 6x2 plus 16x3. That is our objective row. First constraint, x1 minus 4x2 plus 4x3 plus the slack is equal to 2. Second constraint, x1 plus 2x2 plus 2x3 plus the slack is equal to 1. This is the system of linear equations that we start with. Okay, so the solution we read is W1 and W2 are basic. W1 equals 2, W2 equals 1, x1, x2, x3 are 0, and z is equal to 0. Basic variables are W1 and W2. Non-basic variables are x1, x2, x3. Great. Let's apply the simplex method. We're maximizing the objective function. Look at the objective function row. Which variable we can increase to get the biggest bang for our buck to make the objective value better? Let's increase x3. Largest positive objective function coefficient, x3. How much can we increase x3 before we get in trouble? From the first constraint row, we can increase x3 all the way to 2 over 4, 1 over 2 before W1 turns negative. From the second constraint row, we can increase x3 all the way to, again, 1 over 2 before W2 turns negative. So for increase x2, 3, up to the minimum of 2 over 4 from the first constraint row and 1 over 2 from the second constraint row. 2 over 4, 1 over 2. There's a tie, right? So we're going to break the tie arbitrarily. Just arbitrarily, let's say the new value of x3 is determined by the first constraint row. Break the tie arbitrarily. It's both 1 over 2 in both constraints. Break the tie arbitrarily. So let's say that the new value of x3 is determined by the first constraint row. So we're going to do row operation such that x3 appears only in the first constraint row. So the minimum of 2 over 2 and 1 over 2, they are both 1 over 2. So the minimum of the 2 is 1 over 2. Break the tie arbitrarily. Do row operations such that x3 appears only constraint 1. We want x3 to appear only in the third constraint. We want x3 to appear only in the first constraint row. We're going to do row operations such that x3 appears only in the first constraint row. To make x3 to disappear from the objective function row, multiply the first constraint row by -4 added over here. And to make x3 to disappear from the second constraint row, multiply the first constraint row by -1/2 added to the second constraint row. Let's do those row operations. This row times -4 added to the first objective function row. First constraint row times -4 added to the objective function row. 4x4 times x1 times -4 is -4x1 plus another 12x1. That is going to be 8x1. Let's keep going. -4 times -4, that is going to give us plus 16x2 plus another 6x2. That's going to give us 22x2. 4x3 times -4 is -16 plus another 16x3. x3 goes away. That's what we're trying to do. W1 times -4 is -4W1 plus 0W1 -4W1. No W2, no W2, no W2. On the right-hand side, 2 times -4 is -8, z -8. Take the first constraint row, multiply by -1/2, add it to the second constraint row. x1 times -1/2 is -1/2 x1 plus another 1x1. That's going to give me 1/2 x1. -4 times -1/2, that is going to give us plus 2x2. plus another 2x2, that's going to give us 4x2. 4x3 times minus 1/2 is minus 2x3 plus another 2x3, 0x3, x3 goes away. That's what we're trying to do anyway. W1 times minus 1/2 is minus 1/2 W1 plus 0 W1 minus 1/2 W1. No W2 plus another W2. W2 here. 2 times minus 1/2 is minus 1 plus another 1. That's a 0 here. We want x3 to appear in the first constraint row with a coefficient of 1. So multiply the first constraint row by minus 1 over 4. Minus 1 over 4 x1 minus x2 plus x3 plus 1 over 4 w1 equals 2 times 1 over 4 is 1 over 2. This is the next slope equations we reach. Okay, what is the solution we reach here? X3 and W2 are basic. X3 is 1/2. W2 is 0. X1, X2, and W1 are 0. And Z is equal to 8. And our basic variables are X3 and W2. And non-basic variables are X1, X2, W1. Great. Have we reached the optimal solution? No. There is a decision variable we can increase to make the objective value larger. So we haven't reached the optimal solution yet. So let's go ahead and apply the simplex method to make our objective function better and better. So we're going to increase x2 to make the objective value larger. From the first constraint row, x2 appears with a negative coefficient over here. So now I can increase x2 as much as I want without x3 turning negative. So from the first constraint row, I can do as much as I want. I can increase x2 as much as I want. From second constraint row, right now x2 is 0, wt is equal to 0. So that they add up to 0. So I'm trying to think about how much can I increase x2 before w2 turns negative. If I increase x2 just a little bit, if you increase x2 to 0.1, this is minus, if you increase x2 to just 0.1, this is 0.4, then w2 has to be equal to minus 0.4. So then the largest I can increase x2 before w2 turns negative is all the way up to 0, and that's it. So the first constraint says you can increase x2 as much as you want without getting in trouble. The second constraint says you can increase x2 all the way up to 0 before w2 turns negative. If x2 is just a little bit above 0, then to make sure that these two add up to 0, w2 has to be negative. So from second constraint, we can increase x2 up to at most 0 before w2 turns negative. So then we're going to increase x2 all the way up to 0, all the way up to 0. In this case, the new value of x2 is going to be determined by the second constraint. So we're going to do row operations such that x2 only appears in the second constraint. So do row operations such that x2 appears in constraint 2 only. Let's do those row operations. So I want to make sure that x2 appears only in the second constraint row. In order to make that happen, we're going to take the second constraint row, multiply it by minus 22 over 4, and add it over here. And minus 22 over 4 is minus 11 over 2. Good. If I want x2 to disappear from the objective function row, take the second constraint row, multiply it by 22 over 4, minus 22 over 4, and add it over here, and 22 over 4 is minus 11 over 2. Likewise, if I want x2 to appear only in the second constraint row, take the second constraint row, multiply it by 1 over 4, add it over here so that x2 disappears from here. So multiply the second constraint row by 1 over 4, add it over here so that x2 disappears from the first constraint row. Let's do those row operations. Okay. Minus 11 over 2 times 1 over 2. That is going to give us minus 11 over 4 plus another 8 on top of that. Minus 11 over 4 plus 32 over 4, minus 11 over 4 plus 32 over 4, that's going to give me 24 over 4. 21 over 4. Next one. Let's keep going. 4 times minus 11 over 2, that is going to give us minus 22 plus 22x2. x2 goes away. That's what we're trying to do. No x3, no x3. no x3 over here, minus 1 over 2 W1 times minus 11 over 2, that is going to give us plus 11 over 4. Another minus 4 W1 on top of that. Plus 11 over 4, minus another 4 or minus 4 W1, 11 over 4, minus 16 over 4, that is going to give us minus 5 over 4 W1. W2 times minus 11 over 2, minus 11 over 2 W2, plus no W2, minus 11 over 2 W2. What do we get on the right-hand side? 0 times minus 11 over 2 is 0, plus another minus 8, z minus 8. Great, let's keep going. We're going to take the second constraint row, multiply by 1/4, add it to the first constraint row. 1 over 2 x1 times 1 over 4, that is 1 over 8, 1 over 8, plus another 1 over 4 x1, 1 over 8 plus 1 over 4, that is 1 over 8 plus 2 over 8, that is going to be 3 over 8 x1. Keep going. 4x2 times 1 over 4 is x2, minus another x2, x2 goes away, that's what we're trying to do. No x3 plus another x3, that's just an x3. Minus 1 over 2 W1 times 1 over 4, that is minus 1 over 8. Minus 1 over 8 plus 1 over 4, 1 over 4 minus 1 over 8, that's going to give us 1 over 8. It's a 2 over 8, 2 over 8 minus 1 over 8, 1 over 8. W2 times 1 over 4 is 1 over 4 W2 plus no W2, that is 1 over 4 times W2. On the right-hand side, 0 times 1 over 4 is 0 plus 1 over 2, 1 over 2. And we want x2 to appear in the second constraint row with a coefficient of 1. So multiply the second constraint row across by 1 over 4, so that x2 has a coefficient of 1 in the second constraint row. 1 over 8 x1 plus x2 minus 1 over 8 w1 plus 1 over 4 w2 is equal to 0. Okay, great. Okay, what is the solution we reached? Our basic variables are x3 and x2. So x3 is equal to 1/3, x2 is equal to 0, x1, w1, and w2 are 0, z is equal to 8. And again, let's mark our basic variables. Basic variables are x3 and x2. Non-basic variables are x1, w1, and w2. Good. Let's see what happened in these two iterations. In the previous iteration, our objective value was 8. We did these row operations. What did I get? What is my current objective value in the next iteration? It's 8. So I did this simplex iteration. The objective value did not improve. Let's also look at the values of our decision variables. In the previous iteration, x1 was 0, x2 was 0, x3 is equal to 1/3. In the current iteration, x1 is 0, x2 is 0, x3 is equal to 1/2. In the previous iteration, x1, x2 are 0, x3 is equal to 1/2. And in the current iteration, x1 is 0, x2 is 0, x3 is equal to 1/2. So now from one iteration to the next, not only that the objective value did not change, the values of my decision variables did not change either. So the only thing that changes the classification of my variables as basic and non-basic. In the previous iteration, x3 and w2 were basic. In the current iteration, x3 and x2 are basic. Okay, so now we're starting to think like we broke the simplex method. I did an iteration of the simplex method. The objective value didn't improve. The values of my decision variables didn't improve. I know that I haven't reached the optimal solution. So the simplex method is spinning its wheels, not improving the objective value, but it hasn't reached the optimal solution either. The values of my decision variables are not changing. The only thing that's changing is the classification of my decision variables are basic and non-basic. So we're starting to worry about this a little bit. It looks like we broke the basic method, we broke the simplex method, but it did not break. It's just because of the fact that we have a basic variable w2 that takes the value 0. And the next iteration, we still have a basic variable x2 that is taking value 0. So the solutions that we're hitting are degenerate solutions. We're hitting solutions where basic decision variables takes value 0. Then we know that if I hit a degenerate solution, the simplex method may spin its wheels for a while, but I know that I'm eventually going to get out of that degenerate solution. So then let's keep ahead and apply the iterations of the simplex method as we know it. with the hope that we're going to get out of this spinning its wheels situation. Okay, did I reach the optimal solution in the second in this current system of equations? No. There is a decision variable x1 that I can increase to make the objective value larger. Let's go ahead and increase x1. How much can we increase x1? From the first constraint row, we can increase x1 all the way up to 1 over 2 divided by 3 over 8. From the second constraint row, I can increase x1 to 0 divided by 1 over 8. The minimum is 0. So now we're going to go ahead and increase x1 all the way to 0. In this case, the new value of x1 is determined by the second constraint row. So do row operations such that x1 appears in the second constraint row only. So the minimum occurs in the second constraint row. So do row operations. So the new value of x1 is determined by the second constraint row. Do row operations such that x2 appears only in the second constraint row. Good. So I want to make sure that x1 appears only in the second constraint row. I want x1 to disappear from the objective function row. In order to do that, if I take the second constraint row and multiply it by minus 42 and add it over here, x1 is going to disappear from the objective function row. Good. I also want x1 to disappear from the first constraint row. If I take the second constraint row, multiply it by minus 3, add it to the first constraint row, then x1 is going to disappear from the first constraint row. Let's do those row operations. One over 8 times minus 42, that is going to give me minus 42 over 8. That is minus 21 over 4 plus 21 over 4. x1 goes away from the objective function row. That's all we want. x2 times minus 42, that's minus 42 x2 plus no x2. That is going to give me minus 42 x2. No x3, no x3, so no x3 in the objective function row. 1 over 8 times minus 1 over 8 times minus 42. So that's going to give me 42 divided by 8. 42 divided by 8, that is 21 over 4. That's another minus 5 over 4. 21 over 4 minus 5 over 4, W1. That's going to give me 16 over 4. That is a 4. 4 W1. Good. Minus 42 times 1 over 4 for W2. That is going to give us minus 21 over 2. Minus 21 over 2 plus another minus 11 over 2 W2. That is going to give us minus 21 over 2 minus 11 over 2. That's going to give us minus 32 over 2. That is a minus 16 W2. What do we have on the right-hand side? 0 times minus 42 is 0, minus another 8, z minus 8. Okay. We want x1 to disappear from the first constraint row, multiply the second constraint row by minus 3, add it to the first constraint row. 1 over 8 times minus 3 is minus 3 over 8, plus 3 over 8 x1. x1 disappears from the first constraint row. x2 times minus 3 is minus 3 x2, plus another 0 x2, minus 3 x2. 0 x3 times minus 3 is 0 x3, plus another x3, x3. 1 over 8 minus 1 over 8 w1 times 3, that is 3 over 8 w1. Plus 1 over 8 W1, 3 over 8 plus 1 over 8, that is 4 over 8, that is 1 over 2 W1. 1 over 4 W2 times minus 3 is minus 3 over 4 W2, plus another 1 over 4 on top of that, minus 3 over 4 plus 1 over 4, that is minus 2 over 4, that is minus 1 over 2 W2. On the right-hand side, 0 times minus 3 is 0, plus 1/2, that's a 1/2. Let's keep going. We want x1 to appear over here in the last constraint row with a coefficient of 1. So multiply everything across by 8. x1 plus 8x2 minus w1 plus 2w2 is equal to 0. Good. In this solution that we reach, what are my basic variables? x1 and x3. Let's read the solution. x3 is equal to 1/2, x1 is equal to 0, x2, w1, and w2 are non-basic variables. They're all equal to 0. Z is equal to 8 as well. Let's mark our basic and non-basic variables. Basic variables are x3 and x1. And non-basic variables are x2, w1, x2, w1, and w2. x2, w1, and w2. Good. What happened? Still, we're spinning our wheels. The objective value in the previous iteration was 8. The objective value in the previous iteration is still 8. My decision variables in the previous iteration was x1 was 0, x2 is 0, x3 is equal to 1/2. In the current iteration, x1 is 0, x2 is 0, x3 is equal to 1/2. So my objective function did not get better. The values of my decision variables did not get better, did not change. The values of my decision variables did not change. The objective function did not get better. The only thing that changed again is the classification of our decision variables as basic and non-basic. In the previous iteration, x3 and x2 were basic. In the current iteration, x3 and x1 are basic. So we're still spinning our wheels. And looking at the objective function row, do I look like I reached an optimal solution? No, there's still a decision variable, supposedly I can increase to make the objective value larger. So let's again have faith in the simplex method. Let's keep on applying the iterations of the simplex method with the hope that, with the faith that eventually we're going to get to the optimal solution. Okay, so now looking at the objective function row, which decision variable we can increase to make the objective function better, we can increase W1. Oh, increase W1. How much can we increase W1 before we get in trouble? From the first constraint row, we can increase W1 up to 1/2 divided by 1/2, that is a 1. From the second constraint row, how much can I increase W1 before I get in trouble? W1 appears with a negative coefficient in the second constraint row. I can increase W1 as much as I want without x1 turning into negative. So then we can increase x1 up to, let's say, 1/2 divided by 1/2, which is 1. From second constraint row's perspective, we can increase W1 as much as we want without x1 turning into negative. Okay, so from first constraint row, we can increase x1 all the way to 1 before x3 turns negative. From second constraint row, we can increase w1 as much as we want without x1 turning negative. So we can increase w1 all the way up to 1/2 divided by 1/2. So in that case, the new value of w1 is determined by the first constraint. So we're going to do row operations such that w1 appears only in the first constraint row. Let's do those row operations. I want w1 to appear only in the first constraint row. To make w1 disappear from the objective function row, take the first constraint row, multiply it by -8, add it to the objective function row. And also to make w1 to disappear from the second constraint row, take the first constraint row, multiply it by 2, add it to the second constraint row. Let's do those row operations. Take the first constraint row, multiply by -8, add it to the objective function row. -3 times -8 is, -3 times -8 is, that is plus 24, 24x2, minus 42x2, minus 42 plus 24, that is minus 18x2. x3 times -8 is minus 8x3 plus 0x3, that is going to give us minus 8x3. 1/2 w2 times -8, minus 4w1, I'm sorry, 1/2 w1, 1/2 w1 times -8, that is minus 4w1, plus 4w1, that's 0w1. 0w1 goes from the objective function. That's what I wanted anyway. Minus 1/2 w2 times minus 1/8. That is plus 4w2 minus another 16w2. That is going to give us minus 12w2. What do we have in the objective on the right-hand side of the objective? 1/2 times -8 is -4. 1/2 times -8 is -4 plus another -8 on top of that, minus 12 in the objective function. Let's make sure W1 goes away from the second constraint row, multiply the first constraint row by 2, add it to the second constraint row. No x1 times 2 is no x1 plus another x1 over here. Minus 3x2 times 2 is minus 6x2 plus another 8x2. That's going to give us 2x2. x3 times 2 is 2x3 plus 0x3. That's going to give us 2x3. Half W1 times 2 is W1 minus another W1. W1 goes away. That's what we're trying to do. Minus half times W2 times 2 is minus W2 plus another 2W2. That's going to give us plus W2. And on the right-hand side, 1/2 times 2 is 1 plus another 0. That's a 1. And we want W1 to appear in the first constraint row with a coefficient of 1. So multiply everything in the first constraint row across by 2. Okay. In that case, we're going to get minus 6x2 plus 2x3 plus W1 minus W2 is equal to 1 on the right-hand side. Let's check our arithmetic. We seem to be doing okay. Good. What is the solution we read? The basic variables are W1 and x1. So the solution we read is W1 equals 1, x1 equals 1, x2, x3, and W2 are 0, and z is equal to 12. So what happened? The objective value got better. The objective value got better. And our decision variables values also changed, right? In the previous iteration, we had x3 equals 1/2. So now x3 snapped to 0. And let's note our basic variables here, W1 and x1. Non-basic, x2, x3, and W2. Okay. This is, and did we reach the optimal solution? If you look at the objective function row, all objective function coefficients are negative or 0. So there is no decision variable we can increase to make the objective value better. So this is the optimal solution to the linear program. Great. Good. So then the third anomaly we saw is degeneracy. What is degeneracy? During the course of the simplex method, we may run into a solution where a basic variable takes exactly value to 0. If you run into a solution where a basic variable takes exactly value 0, we say that that solution is degenerate. If the simplex method runs into a degenerate solution, it may spin its wheels for a while. It may do a few iterations where the objective value doesn't improve at all, but that's okay. Keep on applying the iterations of the simplex method. Eventually, you snap out of that degenerate solution. You eventually start making improvements, and you will get to the optimal solution. So that is the last anomaly or interesting thing I'm going to say that you can face during the course of the simplex method. So we talk about how we can detect unbounded linear programs. At any iteration of the simplex method, if you have a non-basic variable with a strictly positive objective function coefficient, so that we can increase that non-basic variable to make the objective value better. And also this non-basic variable has all negative or zero constraint coefficients. So we can increase that non-basic variable without violating any of the constraints. Then we have an unbounded linear program. We also saw how we can detect multiple optimal solutions. At the final iteration of the simplex method, if you have a non-basic variable with a 0 objective function coefficient, then we have multiple optimal solutions. At the final iteration of the simplex method, if you have a non-basic variable with a 0 objective function coefficient, if you increase that non-basic variable, the objective function doesn't go larger, but it doesn't go worse either. So if you go ahead and increase that non-basic variable, you run into multiple optimal solutions. You generate multiple optimal solutions. And lastly, we talked about degeneracy. Degeneracy refers to the situation where a basic variable takes exactly value 0. If your simplex method hits a degenerate solution, it may spin its wheels in a few successive iterations, but eventually snap out of that degeneracy and get to the optimal solution. Okay, let's wrap up here.